Okay, good afternoon. This lecture is about hip resurfacing. And hip resurfacing is a different type of surgery and hip replacement than the traditional hip replacement. With a normal hip replacement, you have a stamped implant and a cup, usually with polyethylene. And in this case, in the hip resurfacing case, we only replace the cartilage. That's the aim of hip resurfacing. That's why it's called hip resurfacing. Okay, so companies have come up with all kinds of different hip resurfacings. So a hip resurfacing consists of a very large metal head in a metal cup. So it's a metal-on-metal bearing, yeah, and they look alike, but they are all slightly different. They are different in material manufacturing, also in tolerances and in design. So this is how a hip resurfacing looks like, and it doesn't have this big stem, right? This is a hip resurfacing, and it looks a little bit like the Joydeep prosthesis that I showed you before. That was this prosthesis. That was also replacing the femoral head. But in this case, we have a very tight manufacturing tolerance because we have improved. Okay, I will show you now a video how a hip resurfacing is done.
This animation will show how a diseased or damaged hip can be treated with the hip resurfacing procedure. Click the navigation arrows below the animation screen to play, pause, rewind, or fast forward the animation. Hip is a ball and socket joint. The ball is formed by the top of the thigh bone or femur. This fits into the hip socket or acetabulum, which is part of the pelvis. Normally, the ball moves smoothly in its socket on a lining of shock-absorbing cartilage. If the cartilage is worn away, the joint can become painful. Hip resurfacing is usually carried out under a general anesthetic, which means that you'll be asleep throughout the procedure and feel no pain. Alternatively, surgery can be carried out under an epidural or spinal anesthetic, using local anesthetic injected into the lower back that completely blocks feeling from the waist downward below the site of the injection, but you remain awake. Once the anesthetic has taken effect, your surgeon will make a cut along the area and thigh. The damaged surface of the ball will be removed and it will be reshaped to fit the new implant. Damaged bone and cartilage will be removed from the socket. A metal cup will be fitted into the hip socket. The metal cap replaces the damaged surface of the ball at the top of your thigh bone. When the joint has been resurfaced, the cut is closed with stitches or clips. This is the end of the animation. Click on the animation screen to watch it again.
Okay, so you can see relative to a total hip replacement, the amount of bone what is removed is dramatically less. And that's the attractive part. So if a hip resurfacing fails, you can always transfer it to a normal total hip replacement because the bone, you have still bone to fixate. Okay, so for the resurfacing, you have an acetabulum and an femoral component. It preserves the femoral neck, whereas traditionally we would cut away the neck. It's a metal-on-metal bearing. It's been in use now for 15 years, and it's usually indicated for young and active patients, and that has to do with the big ball that generates a stable joint and allows for a large range of motion, like the athletes and the ballet dancers that we talked about before. There are no large deformations accepted. That means that if the joint is deformed dramatically, you cannot put in this implant because you cannot do any corrections. If you have the stem, you can rotate it a bit, you can make some corrections. Okay? On the positive side, preservation of that femoral neck is important for perhaps a future revision surgery. The largest size reduces the risk of dislocation because it is not easy to pop it out. You can imagine that because it's a very big head. It is more likely, and studies have proven that the gait and the movements of resurfaced patients is more natural because you replace really the articular joints rather than having an artificially small head. And it's for younger patients with good bone strength because you can imagine that you cannot fixate this well on an osteoporotic femur because then it will break out quite easily. So on the contrast side, you have a metal-metal articulation, and you could have these metal ion and particle release due to wear. The surgeons cannot use screws to fixate the cup. We talked about that before. Sometimes you want to use a screw, but that's not possible because then the screw will interfere with the head, right? So that's not possible. So this is always inserted with an interference fit and not with screws or spikes. And it's not for older patients or pregnant patients because of the cobalt chrome release that we talked about before, or for poor bone strength. Okay, so we're going to talk about wear and lubrication, surface replacement and stress shielding. We talked about stress shielding before, but the resurfacing has a special aspect to it, and how these implants fail. Okay, so in terms of lubrication, what you want is to have a smooth bearing, okay? And so what you do not want is a dry running bearing because then it looks like a tire on the road. If it's lubricated, it's slipping tremendously, and that's what we want to achieve between the head and the cup. Okay, so we want to have fluid film lubrication. So this could be the ball of the head, this could be the cup. And if you rotate this, and especially when it's big, you will draw fluids inside, and by drawing the fluid inside, you will separate the ball from the cup. So there is a built-in pressure due to the rotation, and that is called fluid film lubrication. And the bigger the head, the better it is, and these resurfacing have big heads. So the original idea was that this would be very successful because we would have fluid film lubrication. More recently, we know that we do not move all the time. I mean, if you stand and watch a cricket game, for example, there will be no fluid flow because you're standing still. We'll have metal-on-metal contact. Right? So in a hip simulator, I've shown you the picture before, it's moving all the time. So that's not realistic. You should have start-stop events in the simulators as well. So people work on that now as well to include start-stop events. Okay, so people have been publishing about the clearance between the head and the cup. So the smaller this gap, the better the lubrication is. Because you can imagine if this ball is very small, the power you need to have the fluid film is too large. So there will not be fluid separation. People have looked in the literature, have looked at patients with a certain clearance between the ball and the socket. And if the clearance is very small, the wear rate is also very small. So you should have a bearing with very small clearance, but of course it's limited by the manufacturing tolerances. We're talking about here 70 microns. So if the tolerance in the manufacturing process is 100 microns, you should not design it like that, because then it could jam, you know, and if it jams, then the bearing is of course failing. Surface replacement and stress shielding. So we looked at this picture before. So you can see here that bone adapts according to Wolff's law to transfer stresses. We have seen this, that stresses are contained in a prosthetic stem. Yeah? Here you see a micro CT finite element model. So we have a proximal femur, and we made a micro CT scan, or Bert van Rietbergen at the University of Eindhoven did that. And he can create a model and load the model and calculate how loads are transferred. Then he put on a resurfacing. And he loaded that, and he can calculate how load is transferred to the bone. So what he calculates is that underneath the cup there might be some stress shielding. So here you see that stresses are not busy graph, but you can see a lot of variation. What you also can see is, for example, 6 millimeters of cement thickness instead of 2. So the cement mantle is just not correct. So he found very variable cement thicknesses. In general, there was too much cement penetration, and little cement on the sides. I will show an example. And only 30% reached the cement objective of that 2 millimeters. So the cementation technique or the instrumentations for the surgeons was absolutely inadequate. Now here you can see an example. So this is an X-ray of a cut that he made. And here you can see an example. So what you see here is that this is in the order of a centimeter. So what it tells me is that perhaps this plant should have been positioned here. So it was not pushed on the bone with enough power, or the cement was already hard so that the surgeon couldn't get it on. So this is far too thick. What you also see here is there is no cement at all. And here there is cement, so maybe it's asymmetrically positioned, but this should have also been cement. So this is too thick, which increases the offset. So because it makes the neck longer basically and causes pre-stress in the joint, whereas the aim is that you reconstruct exactly anatomically the cartilage layer, and now you have suddenly a centimeter longer neck. You see here the uncovered bone, and you see here a few other examples. So this is also far too thick. So I don't think that the components are fully seated. So it should have been further on the neck. What they also found is, in some cases, this line. Yeah, here you can see that, and that is in 39% a kind of a fracture, because this is soft tissue. Here you can see the soft tissue. So it seems to be a pre-existing fracture, and probably the patient has pain because it moves. This is bone, and then it can toggle a little bit. So the patient comes to the doctor with pain because this moves around here. And in 39% of the cases, that was the phenomenon. So, yeah, this is a real failure mechanism. And apparently the stresses are too high because it toggles all the time. Now, I've shown you this slide before, and this is really a problem for the resurfacings. And this is the pseudotumors that we talked about earlier, generated by the wear particles of the cobalt chromium. Yeah, and the soft tissues respond to that by kind of dissolving. And we couldn't see that on X-rays, but we can see it on MRI scans now. So if you look at the survival for failures, they are higher in women than in men. And that's probably because of the size, but also because of the bone quality. Yeah. So this is the failure rate of females relative to males. Whereas with traditional hip implants, we don't see that difference. So this implant is very sensitive to bone quality and positioning. And when we look at the diameter size, so the size of the head, you can see that the small diameters fail earlier. Yeah, and that is also probably because the safety factor of these small implants is smaller, and then they fail quicker. Yeah, so the bigger heads, they do better, and the bigger heads tend to be implanted in males with very good bone quality, and so they do better. I should say that not all hip resurfacings are the same. For example, the Birmingham hip resurfacing that is shown here shows a survival curve which is like this. So after 14 years, it's doing very well. Yeah. Whereas this is the traditional total hip replacement surviving curve in the Swedish register. So there are different designs and they do not do so well, but some of them still are better than others. And that's shown here. So this is results from the England and Wales register. That's a huge register in the UK. You see that the Birmingham hip resurfacing is doing much better than 2 other resurfacings. Yeah, and in the Australian register, it's the same. Yeah. So, for example, the ASR, that's from Johnson & Johnson, that is failing far too much, and it's also taken off the market. And there are a lot of patients that have to come back to the clinic. They need to check up. It's very costly, and Johnson & Johnson has to pay for that. Sometimes they need a revision because they see on the MRI scan the pseudotumors, and Johnson & Johnson has to pay for that. So it's a huge thing. But the Birmingham hip resurfacing is still doing well. And I told you already before, this is a metal-on-metal bearing. In some countries, for example in Holland, they decided not to do metal-on-metal anymore. They first wait until there is bigger proof that the Birmingham hip resurfacing is actually doing so well. And then maybe they will release metal-on-metal Birmingham hip resurfacings in Holland. So some of the causes for these neck fractures that I showed you are uncovered ream bone. So basically, if you do not put it well enough, you ream too much, and there is bone. So you ream the bone, and if you do not put the cap enough over it, there will be bone exposed that you have reamed. So that's not good. That's not good. If you leave the component too high, due to excessive cement use, notching of the neck, which means that the cup is hitting the bone, basically. Bad bone quality, impingement, so impingement against the cup, and just a trauma, just an accident, for example. And of course, it could be due to cementing errors that we have shown before. And the biggest concern is wear and subsequent pseudotumors. Thank you very much.